Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Advancing Power Circuits, Silicon Carbide JFETs in Solid-State Circuit Breakers and Hot Swap Applications, brought to you by Tech Online, onsemi, and broadcast by AspenCore. I'm Colleen Heckman, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the blue paperclip icon at the bottom of your screen. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window, and then click the Submit button. If you're experiencing any technical problems, you may also type that same issue into the Q&A text area, hit the Submit button, and we'll be glad to offer one-on-one assistance. I would also like to encourage our attendees to complete the feedback survey on the right side of your console. Be sure to complete that before you log off today, and thank you in advance. And now, onto the presentation, Advancing Power Circuits, Silicon Carbide JFETs in Solid-State Circuit Breakers and Hot Swap Applications. Discussing today's topic is Jonathan Dodge, Applications Engineer, Power Solutions Group at onsemi. Jonathan earned a bachelor's degree in electrical and electronics engineering from Oregon State in 1992 and a master's in electrical engineering from the University of Idaho in 2000. Jonathan is a licensed professional engineer in the state of Oregon with more than 30 years experience, including design of analog, digital, and power electronics, working with power levels ranging from 1.5 to 500 kilowatts in renewable energy and other applications. It's with great pleasure I now hand things over to Jonathan to begin. Jonathan, take it away.
Thanks, Colleen, for that nice introduction. Well, let me introduce our topic here. So we're talking about solid-state circuit breakers, and in particular, replacing electromechanical breakers, where the heat budget is typically very limited. And we'll also briefly talk about hot swap applications, where someone wants to remove or insert a power supply in a rack of other power supplies that are already powered up. First, let's talk about why would we want to replace an electromechanical breaker with a solid-state circuit breaker. Well, the main reason is that the solid-state circuit breakers are so much faster. They switch about 1,000 times faster than electromechanical. You can detect a fault and respond and shut down about 1,000 times faster. And so what that means is that there's less time for energy to flow into a fault, and you can completely eliminate arc flash. There's just simply too little time for them to form. So this is significantly safer, especially in DC applications, but also in some AC applications. Another advantage of solid-state circuit breakers over electromechanical is the service life. When switching under voltage and current, electromechanical breakers often degrade because of arcing in the contacts. And here's a chart showing that effect. So as either the voltage or the current increases, the number of cycles that you can switch under load decreases. Well, this is not the case with solid-state circuit breakers. As long as you remain within reasonable energy limits, there are unlimited switching cycles with solid-state circuit breakers. Another advantage is the control options because it's electronically controlled. So you can have better fault selectivity. By that, you can set the trip threshold based on current profile. So if you have a very unusual current profile, it looks hazardous, you can turn off sooner instead of simply setting your trip threshold very high. You can have smart control for energy saving, so you can coordinate things, for example, a water heater with other appliances, and keep your peak power consumption under control that way. You can monitor and reset. You can even do automatic resetting. Now, this is a big advantage in some cases, so no one needs to actually go down and physically flip the breaker back on. You can have diagnostics. You can even do soft start, for example, if you're having a motor load that needs to start with high current, you can build in soft start features into the solid state circuit breaker. And of course, in the breaker itself, there's no arcing. So your electromechanical breaker inside, when it switches under load, there'll be an internal arc, and that must be suppressed. Well, there's no need for that suppression because there's no arc generated in the solid state circuit breaker. So an important development is the emergence of standards for solid state circuit breakers. And this allows manufacturers to design their products to these standards and then go through agency approval and put their circuit breakers on the market. So I'll go through now 4 reasons for using silicon carbide JFETs in solid state circuit breakers. So when replacing electromechanical breakers, you're typically replacing a breaker that goes in a panel with many other breakers, and there's no place to put any heat, or very little. And so the main concern of a manufacturer of this kind of breaker is heat generation. So all power semiconductors, as they allow current to flow through them, have some heating. And that's called on resistance. So you need to have the minimum on resistance possible. And so that is what the JFET provides. So here's an example. So we have here a silicon carbide JFET. Actually, it's a combo JFET. I'll explain what that is. But it's a 750 volt rated part, 5.4 milliohm on resistance in a toll package. That's a surface mount TO leadless package. So that part has less than half the on resistance of the closest competing part in that same package. That's a big advantage for making these solid state circuit breakers. How is the JFET so low in RDS on resistance? Well, it's because it's a JFET. There is just a direct path for current to flow between the power terminals, source and drain. There is no PN junction. There's no diode in the path of the current. And there's also no surface current. It's a wide channel. So what we're looking at here in this drawing is a cutaway view of a single JFET cell. There are thousands of these in parallel on a JFET chip. And you can see the current path nice and wide straight through. It flows through highly conductive silicon carbide material. So this gives the JFET the lowest possible on resistance for a given voltage rating. These JFETs have been manufactured for over 10 years now, so there's quite a bit of know-how involved. One of the processes is thinning the wafers, and so that's a proprietary process that helps to result in a very low on resistance. And then with the JFET is normally on. So with no voltage applied to the gate, the channel is open and current can freely flow. But if you apply slightly positive voltage to the gate, you actually turn on the JFET a little bit more, and that gives you another approximately 15% reduction in on resistance. And so we'll use a simple resistor to do that with. There's no special circuitry required. To turn the JFET off, you pull the gate to source voltage negative, and that turns it off. So the silicon carbide JFET is normally on, but in many cases, in fact, in most cases, we want the device to be off. So how can that be done? So the way to do that is to connect the silicon carbide JFET in series with a low voltage rated, normally off silicon MOSFET. And then we connect the JFET gate somehow or other from the JFET gate to the MOSFET source. Make a connection there. It can be either a direct short as I'm showing in the diagram on the left. This would be how it's done in the standard cascode products, which are intended for switch mode applications. And if you directly connect the JFET gate to the MOSFET source, the switching speed will be too fast for circuit breakers and relays, at least 50 times too fast. And it's impractical to slow them down in that scenario. So what is done instead on the right, where we have the silicon carbide JFET and its gate is brought out and connected again in series with the normally off silicon MOSFET. And then we can choose our own resistance or impedance to connect between the JFET gate and the MOSFET source. So this could be just a resistor, or it could even be just a Zener diode, depending on how you want to drive the two parts. So now we have two devices, which is fine for cost. Both especially the silicon MOSFET is very low cost. But now you have two parts that takes extra space. So let's talk about how we deal with that. This brings us to the second main reason for considering silicon carbide JFETs in solid-state circuit breakers. So what is done at onsemi is we stack the chips. So we'll have two chips in a single package. This is called a combo JFET. So this is where we have the silicon carbide JFET still connected in series with the normally off silicon MOSFET. But instead of tying the gate of the JFET to the MOSFET source inside the package, the JFET gate is brought outside the package so that the user can connect it however is appropriate for their application. And then the MOSFET gate is also brought out. So we have the picture on the right of what it looks like inside the part. We have the blue chip, which is the silicon carbide JFET. It is silver sintered to the copper of the package. And then the MOSFET chip, the yellow chip, is sintered on top of the JFET chip. And then the gate of each chip is brought out separately to separate pins. This is a combo JFET. This is a process that has been used for many years. Here's an example of this type of technology is the 750 volt 5.4 milliohm JFET plus MOSFET in a toll package. So another way to save on space is to reduce the number of parts in parallel. So here's an example of a 240 volt AC circuit breaker rated at 20 amps with a 1.2 factor overload for 2 hours. So if we look at the power dissipation, we can calculate the required RDS on, and we're operating, assuming that we're operating at temperature, so we'll say 100 degrees C. So of course, these parts have increasing on resistance with temperature. So if we look at that 750 volt combo JFET, so we have 7.8 milliohms at 100 degrees C. So that would work, but to block AC, we need to connect back to back. That means we have two ports in series with their sources connected together, which doubles the conduction loss. So therefore, our on resistance number needs to be half. So we need two in parallel. Okay, so the solution with the combo JFET is four parts in total. The closest competing part in the toll package would require 5 in parallel, so a total of 10 parts. Obviously, the combo JFET is going to require much less space. Now we come to a very nice feature of the silicon carbide JFET, and that is the ability to sense the JFET's temperature using the JFET itself as the temperature sensor. So as we drive the gate slightly positive, we call that overdriving the gate, We're injecting a little bit of current. Now this is small current, let's say 1 milliamp to 5 milliamp type range. Perfectly safe. But what it does is that causes the gate source voltage on the JFET to be positive, but it changes with temperature in a very predictable way. So what we can do is measure that gate source voltage drop and tell what the temperature of the JFET chip is. Now, if you have a combo JFET and you have no access to the JFET source itself to make that measurement, but that's okay if we have back-to-back connected parts. So here in this schematic, we have JFET and MOSFET in series, and that's copied and mirrored. So it's back-to-back to block AC. So what we'll do is we'll take the measurement from the gate of each JFET to the common source point. And we do that with two different amplifiers. And what ends up happening is the voltage drop across the MOSFETs cancel out. So the result is the average gate source voltage of the two JFETs. And again, that gate source voltage is used to tell what the temperature is of the JFET chips. So now I will share with you a very simple and elegant way to sense the current. So this uses a couple of diodes connected in series with the drain of the JFET or the combo JFET. Now this would be typical of a DSAT arrangement. Now it's not necessary to use the DSAT feature, but if you use a gate driver with a DSAT, you can use its DSAT pin to supply a small current through these diodes D1 and D2. Or you can simply supply that small current from the gate drive power supply through a resistor. In either case, the idea is that you use two identical diodes, D1 and D2. They are capable of blocking high voltage, but again, only a small current flowing in the microamp to milliamp range. You clamp the first diode, D1, and you put an amplifier across it to measure the voltage drop across that diode. That voltage across that diode actually represents the drain source voltage of the JFET, or the combo JFET, assuming the MOSFET is on. So now we know the drain source voltage, and we also know the temperature, and we know the change in RDS on with temperature. So therefore, we can compute the drain current just using Ohm's law. This is very simple, very elegant. So now we can sense both temperature and current with the JFET. No additional sensors necessary. I would like to introduce a concept of temperature compensating the overcurrent sensing. So we made two measurements. We talked about measuring the JFET chip temperature with the JFET itself, and then also the drain current by measuring the drain source voltage using the voltage of the DSAT diode. So with those two measurements, what we can do is combine them along with our overcurrent trip setting and run those to a comparator. So the reason to combine them is that we're somewhat canceling the temperature effects. So on resistance of the JFET or the combo JFET increases with temperature, has a positive temperature coefficient. So at a given current, the drain source voltage measurement will increase as temperature increases. On the other hand, the gate source voltage will decrease as the temperature increases. So if we combine those two, they somewhat cancel each other out. So that helps to compensate for temperature effects. And then you compare your drain source voltage with the trip voltage by comparator, and you have a fast-acting overcurrent trip comparator that is temperature compensated. Now it's somewhat temperature compensated because there's some nonlinearity, especially in the on resistance versus temperature. However, over the operating temperature range that we're typically interested in, it works well enough to be useful so that we can avoid using a microcontroller to make the decision, or even a state machine. It's very fast acting, all analog. This is a conceptual drawing here. There would need to be some additional circuitry to deal with when the JFET turns off and then back on again to handle blanking time and resetting the voltage going into the comparator. So now we come to the third reason for choosing a silicon carbide JFET or combo JFET as replacing electromechanical breakers, and that is dependability. So let's review again how JFET works. So JFET is voltage controlled, and generally speaking, it's biased on and off with the gate source voltage. Drain source voltage also plays a role, but for now, let's just focus on the gate source voltage. So what happens if there's no gate source voltage applied? As I mentioned earlier, the JFET will be on, and you'll have a wide channel for current to flow through. And then as you apply negative gate source voltage, you expand the depletion regions until they meet up, and that blocks current flow. So that's how it's turned on and off. There's no surface current, there's no MOS gate, it's just bulk silicon carbide material. So there's no place for any charges to be trapped, and therefore there's no parameter drift, there's no hysteresis. It's just a very simple construction, and therefore very durable. The gate itself is a PN junction. It is capable of avalanche, and so is the drain source, same PN junction. So you can pull on the gate over a wide voltage range without damaging it. This is quite different from a MOSFET, where the gate voltage is very sensitive, needs to be kept within tight limits. It can also withstand high temperature events within reasonable energy limits without damage to the JFET and without any parameter drift. This includes short circuit and avalanche. So it's a very reliable, very robust technology. It's very well suited for circuit breakers. Another very nice feature of the silicon carbide JFET is a high pulse current capability. So we're looking here at a 4.3 milliohms, 750 volt JFET. This is the same JFET that's in the combo JFET that we have been discussing so far. And its IDM, its peak pulse current rating, is 588 amps. So here we're switching it a little higher. We're switching it at 600 amps with a ramp time of about 24 microseconds. This is basically an unclamped inductive switching setup. We have some cable inductance delivering the power supply voltage to the JFET, and energy stored in that inductance is absorbed partially by the JFET, but then also clamped by some metal oxide varistor in parallel with the JFET. So you'll see that in red, that's the drain source voltage. It rises to almost 600 volt, and there it's clamped by the metal oxide varistors. So anyway, the point of this slide is to show the very high peak current capability of the silicon carbide JFET, which is a big advantage, again, in some circuit breaker applications where it's a requirement to switch very high peak currents, much higher than your nominal current. Another factor for reliability and durability is the voltage rating and how much voltage margin there is. So you need some voltage margin in a circuit breaker application, because what happens is you'll have energy stored in cabling and wires going to and from the breaker. And if you have a fault condition that causes very high current, that energy stored can be very high. So if you switch off with a high current, then energy needs to go somewhere. So you want to dump as much energy as possible into the silicon carbide JFET itself, but it can only handle so much and will not be able to handle all of the energy stored in the cables and wires. So you'll need to add a parallel metal oxide varistor or transit voltage suppressor to handle the additional energy. Well, especially metal oxide varistors, they have a very rounded voltage current curve. So for a high peak current, they'll have a correspondingly high voltage across the metal oxide varistor. And so you'll need a high voltage rating of the JFET to handle that without the metal oxide varistor leaking too much during your normal voltage operating range. So this is the reason why we need a higher voltage rating, and we rate these parts at 750 volts instead of 600 or even 650 volts. It gives you, it's more reliable, and it makes it easier to use with these low-cost clamping devices like metal oxide varistor in a circuit breaker. So we come to our fourth and final reason for using silicon carbide JFET and combo JFET in circuit breakers, and that is that they are easy to use. So here is an example of how to drive the JFETs and the MOSFETs. There are multiple ways to do this, but this is a simple one called direct drive. So here we have two combo JFETs connected back to back, so their sources are tied together. So we have a common source point. So these two parts connected this way can block AC current. So we use standard gate drivers. So we can use an IGBT gate driver, for example, to drive the gates of the two JFETs directly. We're using an overdrive resistor when it's on. So this would limit the current going into each JFET gate, and then the JFETs themselves set the gate source voltage based on their temperature. Turn off is set by adjusting the gate resistor, and that gives you excellent speed control, as mentioned previously, again, because all the output capacitance charge goes through that resistor. So we use a standard gate driver to drive the JFETs. The MOSFETs can be driven by a voltage supervisor or by a separate gate driver. So in this circuit, we're showing a voltage supervisor. The idea being that as soon as gate drive power ramps up, the MOSFETs turn on and simply remain on. And then you control the switching by switching the JFETs on and off. So you can switch this on and off normally or during emergency the same way. And you can also pulse it if you want to do inrush current limiting for charging capacitors. Again, the nice thing about this circuit is that you have very easy speed control just by adjusting the JFET gate resistor. And also, with the MOSFETs turned on and left on, there's no stress on the MOSFETs. All the switching energy goes into the silicon carbide JFETs, which is where you want it to be. So now let's take a quick look at some test results. So here we're showing some test results from a demo board that has two parallel combo JFETs connected back to back. And it's blocking current in both directions and also allowing current to flow in both directions. So, of course, you can only measure temperature while the JFETs are on. And so we have current flowing in both directions. And then we compare that against a calibrated temperature versus gate source voltage curve. And that gives us the final temperature measurement here shown in the graph on the left. So this is using the two amplifier approach. And you can see it's nice and linear. It results in a very easy way to measure the temperature of the JFETs. On that same board, there are two ways to measure the current. One is with a shunt resistor, and the other is using the drain source voltage method with a DSAT diode setup. So you can see on the left, this is current measured with the shunt resistor, and as expected is very linear. And the chart on the right shows current using the drain source voltage measurement method and combining it with the temperature of the JFET chip. So here you can see it is not as linear. There's some nonlinearity to it. However, again, for self-protection over current trip, the nonlinearity is not really concerned because you really are concerned about the current near the trip setting, and you can calibrate that to be very precise. Again, using the same board, overcurrent trip was tested, and the protection level was set to about 660 amps. So using some energy stored in capacitors to run the test, current was rapidly increased, and in this case up to about 650 amps. The comparators tripped and then safely turned off. Okay, let's switch topics and talk about hot swap. What is hot swap? So hot swap is where you have a power supply that has capacitors on it that have no charge in them, and you want to insert it into a rack of power supplies that are already running, so they have capacitors that are fully charged. So if you just push in the power supply into the rack without any sort of limiting of the current, you'll have a huge current surge going into the capacitor bank of this new power supply. And that current spike can happen even if there is some charge in the capacitors of the power supply that you're inserting. And those capacitors need to be almost the same voltage on them as what's in the rack to avoid a current spike. So inrush current limiting solves this problem. So here's a chart that shows what happened without current limiting. So you can have a huge spike in current. It could be thousands of amps. And that causes a voltage dip in the system, can reset controllers of the power supplies, causes big problems. You also have a very rapid rise in voltage across your capacitors. That's not so much a concern, but it's the huge spike in current that caused the problem. So generally, it's acceptable to allow the voltage to rise at a much longer time frame than in a few tens of microseconds. So here we're showing in the dashed lines the same curves as on the previous slide, but on a different time scale. And then in the solid lines, we apply some current limiting. So you can see the current is fixed at a low level, and the voltage rises steadily at a much slower rate. And here it's 1,000 times longer charge time. So this would be 30 milliseconds. That's generally acceptable. We limited the current to avoid a hazardous peak. There's no stress anywhere. There's no sudden transients in voltage in the system. So there's a trade-off between the amount of heat generated in your pre-charge device, your current limiting device, versus the charge time. So far, system voltages have been relatively low, often 48 volts. And so inrush current limiting has been handled in a couple of different ways. One is just a simple power resistor across a relay. You close the relay after the capacitors are pre-charged. And the other way is, instead of using a power resistor, you use a silicon-based MOSFET to limit the current. The MOSFET will heat up and charge the capacitors, and then you you might want to bypass that with a relay or just let the MOSFET conduct the current. So moving forward, operating voltages are increasing because of the huge increase in demand for power. And so operating voltages are increasing to 400 volts, and we're expecting them to go even higher. And of course, capacitor stored energy is proportional to voltage squared. So this places stringent requirements on the pre-charge circuit, the inrush current limiting. So it's much more difficult to do this at these higher voltages. And of course, whatever we use to limit the current would be nice to use as a circuit breaker too. Well, this is where the JFET is really a nice part. So again, we're going to use it to pre-charge or inrush current limit. So we're going to put the device in linear mode or active mode. And that requires a wide safe operating area and thermal stability. We want to use the part for short circuit protection and regular overcurrent protection as well. So we need to be able to control the speed to limit the voltage overshoot. We need to be able to handle high peak currents. And then for normal operation, we need super low on resistance to minimize the power loss. We want to take up small space. We want to minimize the number of parts in parallel. All of these requirements combined point us to the silicon carbide JFET. Definitely the most promising technology for this application. So first, let's define what we mean by linear mode, or also called active mode. We're working in this mode for a relatively long time. By long time, that means relative to the thermal response. So heat generated in the chip, going into the package, and then finally going into the heatsink. So this region could be described by these equations listed here on the left. Then the important point is, if you look at the output characteristic, it's where the curves flatten out, and you'll have a very flat, so insensitive to drain source voltage. The current through the JFET doesn't change much with drain source voltage, but it's very sensitive to the gate source voltage. So that's what we mean by your saturation region, active region, also called linear mode, because of the gate source voltage control of the current. So here's an example of how to do inrush current limiting. So we're going to use the JFET as a constant current source with resistor RS as the feedback element. So as current flows from the input HVDC1 through the JFET, through the resistor RS, there'll be a voltage develops across RS. Of course, that's in series with the source of the JFET and the output, the HVDC2. So that voltage across RS sets your gate source voltage, and therefore that sets your current. And so it's constant current until the voltage, the output, it ramps up linearly until it equals the input voltage, at which point the JFET turns fully on. This entire time, Q2, the low voltage silicon MOSFET, that's been kept off after the capacitors are pre-charged on the output. Then you turn on Q2 to bypass the resistor RS and avoid any power loss in it during normal operation. So only the silicon carbide JFET was in linear mode, so only the JFET was developing a significant amount of heat in order to limit the inrush current into the capacitors. So this is another example of how to do the inrush current limiting. In this case, we've added another MOSFET Q3, And this gives us on-off control, basically. So whenever Q3 is off and Q2, of course, then Q1 will also be off and no current can flow at all. In the previous example, you had no control over when the current would begin to flow. Here you can control when it will begin to flow with the addition of Q3. So you keep Q2 off, turn on Q3, and as before, your current will flow through the silicon carbide JFET, through the resistor RS. That sets your current to a constant level until the input and output voltages are equal, at which point, again, the silicon carbide JFET turns itself fully on. And then you can turn on Q2 to bypass that resistor RS and minimize any power loss. So it's very easy to parallel these because you have individual control over each silicon carbide JFET. So here we have feedback control with amplifiers. And this is a normally off configuration. So that's done by having the silicon carbide JFET in series with the low voltage silicon MOSFET that is normally off, and using a Zener diode D2 to connect the JFET gate to the MOSFET source when there's no power to your op amps. That'll keep the JFET off. So this one works similar to the other circuits. It's just that we're using amplifiers for sensing the current across the sense resistor and comparing that with a gate control. So the gate control could be variable in this case. So now instead of a simple constant current charging of the capacitors, you can change the current profile to be whatever you want. For example, constant power or some other scheme. We can also, in this case, overdrive the JFET. Again, with this slightly positive voltage, we're going to inject a small current into the gate and reduce the on resistance by about 15%. And then we can use the temperature sense feature by measuring the gate source voltage as before. So one point to mention here, so this is controlling a single JFET. It's not so easy to parallel the JFETs with a single set of amplifiers here controlling them and get the current to share evenly. And this is true of any field effect transistor. There's variation from chip to chip in the gate source threshold voltage, even from chips that come from the same wafer. And so for that reason, if you're going to parallel the silicon carbide JFETs, but just use a single set of amplifiers for control of all of them, you need to have substantial derating for the current sharing because they will not share evenly. So the way around that is simply to use multiple amplifiers or make sure you have plenty of current derating. So some tests were run on a silicon carbide JFET in series with a MOSFET. In this case, the JFET gate connected through a resistor to the silicon MOSFET source. So this is somewhat a cascade arrangement here. And what we have done here is switch off, actually in this case, the MOSFET, and that turns off the JFET, but the gate current through the JFET flows through that resistor R7. So by changing R7, we change the switching speed of the JFET. So in the charts below, we see 4.7 ohm JFET gate resistance. In the middle is 500 ohms, and then the chart on the right is 100 ohms. Oh, sorry, 50 ohms in the middle, and then 100 ohms on the right. So you can see
In each case, the time division is the same. And you can see the rate of change in the voltage and current decreases as you increase the gate resistance. That gives you a very nice, simple way to control the switching speed of the JFET just by adjusting the gate resistance value. Okay, we're close to the end here, so let's summarize. So what do the silicon carbide JFET and combo JFET bring to the circuit breaker applications? Well, the simple construction delivers less than half the on resistance per package size compared to competing technologies. We have unrivaled durability, and we use off-the-shelf gate drive components, simple to use, very compact, especially with the combo JFET, 2 chips in 1 package. Okay, so we have a very durable part, no drift, no hysteresis. We can combine functions. We measured temperature of the JFET using the JFET itself and current. You have fewer parts in parallel. And we, again, used all off-the-shelf components, nothing special required. So we have, to date, 750-volt JFETs and combo JFETs, as well as 1200-volt rated JFETs and combo JFETs in surface mount and TO-247 packages. And, of course, there are always new parts in development, so stay tuned for that. And with that, I'd like to turn it back over to you, Colleen, and we can take some questions, further discussion.
Well, excellent. Thank you so much, Jonathan, for a great presentation. So, to our audience, we are now moving on to the question and answer portion of our event. If you haven't done so already, please go ahead and enter your question in now. Please note we'll get to as many questions as we can in the time we have left, but if we don't get to your individual question, someone will get back to you after the program is over. So, Jonathan, we have a bunch of questions coming in, so I'm just going to jump right in and see how many we can get to. Our first question asks, as per the EM circuit breaker standard UL 489, the CB should withstand 1000 VAC plus twice the working voltage for 60s. Is the same test applicable for solid state circuit breakers as well? And if yes, then do we need to add multiple JFETs in series to pass this test?
That is a good question. Okay, so for 1000-volt AC, so we need, excuse me, we need a fairly high voltage rated JFET to handle that. Right now in our portfolio, we don't have that. You might want to stay tuned for later, but for right now, we don't have that. And work that has been done in the past involves stacking the silicon carbide JFETs. And that's called a super cascode. So it is possible to do that. So you can stack JFETs in series, theoretically any number, and still use just one low voltage silicon MOSFET to control the entire chain. Actually, I wrote a paper, developed a scheme where instead of a silicon MOSFET, you use an op amp, and you can do analog control over a super cascode. So you can contact me directly if you want more information about the super cascode concept. It does require some tuning to set the switching speed and so on. But it has been done actually up to 40,000 volts. So it does work.
Well, excellent. And speaking of cascode JFET products, does onsemi offer a variety of switch mode cascode JFET products? And why not use one of them for the solid state circuit breaker?
Okay, yeah, I'm glad you asked that because it is possible to take a switch mode cascode, and by that I mean these are silicon carbide JFET in series with a silicon MOSFET, but the JFET gate is directly shorted to the MOSFET source inside the package. That's just a bond wire short. So you have very little control over the switching speed. That's fine for switch mode where you want to switch fast anyway, but in circuit breakers, we typically want to switch at least 50 times slower than in a switch mode application. And it's impractical to slow the part down sufficiently, even adding snubbers and so on. You just can't get there. So the best thing to do is use either JFET by itself or the combo JFET. In either case, you have the JFET gate available, and then you can set the switching speed directly with the JFET gate resistor. And as I mentioned in the slides, a very nice feature of the JFET is that all of the output capacitance, all of the charge for that goes through that gate resistor. So you have very good control over the switching speed.
Excellent. Thank you for that. And again, to our audience, please do go ahead and submit your questions. We'll get to as many as we can. And if we don't get to your individual questions, someone will definitely follow up with you after. So next question asks, how does onsemi approach the current sensing using VDS and TJ compared to traditional shunt resistor methods?
Oh, yeah. Okay, so it's quite different. We're using the JFET itself. Excuse me. So the first thing you need to do is know the temperature, right? You know the temperature of the JFET by using that gate source voltage, and that's just part of the chip design. There's nothing built in. There's no special diode. It's just part of the JFET. So you measure that temperature, and then measuring the voltage across that diode that's connected in series in a DSAT arrangement can indicate the current. Now, as shown in the test results, there's some nonlinearity to that. However, if you want to use it for self-protection, that's fine. You can calibrate that out. And when there's another concept that I just didn't have time to really go into, and that's where you can actually combine the signals. You can combine the gate source measurement with the drain source measurement, and those measurements change in opposite ways with temperature. So you add them together, basically, and they somewhat sort of compensate themselves for temperature. Not completely because of some nonlinearity, but you can still use it within a reasonable range of temperature to do pure analog over current trip detect, so super fast.
Excellent. Thank you. I'm going to try to squeeze in a couple more questions here for you. What is done at the chip level to make the combo JFET have temperature sensing? How is that function integrated?
Okay, yeah. So that again, that's part of this just built into the JFET chip design. So the JFET has that one PN junction. You have multiple connections to it. The gate source connection is the one we're using. And as the chip heats up, that gate source voltage decreases almost linearly with temperature. So it makes it easy to sense the temperature.
Excellent. Thank you. And it looks like we are only going to have time for one more. So let me go ahead and get this one in. What makes silicon carbide JFET suitable for hot swap applications at higher voltages?
Yeah, so the robustness of the JFET is involved there. So the threshold voltage change with temperature is very slight. It can even be perfectly flat depending on the JFET design. And that's an important factor when operating in linear mode, active mode, same thing, because that helps to avoid the hot spotting effect. And so it's more robust that way than some of the MOS-gated devices.
Excellent. And I'm going to squeeze one more in for you just for fun. Is the fit rate of a silicon carbide combo JFET better than the silicon carbide JFET? Or I'm sorry, the silicon FET. You would know. Silicon carbide FET. Yeah.
Silicon FET, yeah, I'm not sure what's meant by silicon FET, but so I don't have any numbers to answer this right offhand, but just looking at let's just look at the construction of the parts. So the highest reliability would be the silicon carbide JFET by itself. Super reliable part. Again, there's no defect sites as part of the manufacturing process. There's no charge trapping. There's no parameter drift. You can really hit it hard. And as long as you don't abuse it too much, don't burn the chip, there's no change in parameters. We've done short circuit tests repetitive like 10,000 in a row, no change in any of the parameters. is a very tough part. So I would say, you know, the reliability, durability of the silicon carbide JFET by itself is the best. When you combine the MOSFET with it, now you have two parts. The MOSFET itself is also very rugged. It's low voltage, super low on resistance. It's a pure silicon oxide gate. There's no parameter drift in the MOSFET either. But now you have two parts. So, you know, just based on the statistical analysis, I would say the silicon carbide JFET by itself is the most reliable.
Excellent. Well, thank you, Jonathan, for a great Q&A and excellent presentation. For more information related to today's webinar, please visit any of the resource links available in your blue paperclip icon at the bottom of your screen. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. So thank you for attending today's webinar, Advancing Power Circuits, Silicon Carbide JFETs, and Solid-State Circuit Breakers and Hot Swap Applications. Brought to you by Tech Online and onsemi. This webinar is copyright 2025 by AspenCore. The presentation materials are owned by or copyright by onsemi, and the individual speaker is solely responsible for his content and opinion. On behalf of our guests, onsemi, I'm Colleen Heckman. Thank you for your time, and we hope you have a great day.